Great. Okay. So, very good morning to all of you. I welcome you in this class. And today we will be talking about, we'll be discussing particle in a three-dimensional box. Now, before we go into the mathematical procedure of particle in three-dimensional box, because it's an ideal system, a three-dimensional box. That means you have a particle, and this particle is in three-dimensional box. So you have x, you have y, and you have z. And within this box, this particle has no potential energy. And this box will have how many faces it will have? It will have 6 faces. So all of these 6 faces will act as walls with infinite potential. So it is practically impossible for this particle to leave this box, because we are assuming that the potential with respect to the walls is infinite. Right? Getting my point? Now, I think before discussing this problem, it would be right to tell you about some of the practical implications of this particle in a box problem. See, this particle in a box can be used to model the free electron theory in conductors. I think right now you are going through solid state physics. So in your course there will be free electron theory. And free electron theory has to be modeled from the particle in a box kind of situation. Because the situation in a metal with an electron in it is same as that of the particle in a box. The electron inside the metal is free. What you assume there, you assume that electron has no interaction with the charge. The electrons in a metal are free. So you can model metals, you can model free electron theory using particle in a box problem. There is another important thing in the modern science, what we call as quantum dot. Quantum dot. And what is this quantum dot? Is that you can treat materials at very, very low scales, at nanoscales. You can treat your materials as quantum dots. And the behavior of electrons in those materials can be modeled. The behavior of the electrons in those materials can be modeled by the problem of particle in three-dimensional box. You cannot explain why the properties of the material change when you take them to nanoscale, right? So this tool, even though it's purely hypothetical in nature, it has a lot to do with practical applications. There is another example of electron gas. You might have heard about white dwarfs in astrophysics. Have you heard about them? Okay, you have heard about black holes, right? So, in case of, so how do you have a black hole? Black holes come in action when? When you have a supernova. You have a star, there's a supernova, right? And now, depending on the size and mass of this star, there is something called as Chandrasekhar limit. And this limit decides whether your star will transform into a black hole or it will transform into a white dwarf. Okay? So, white dwarf is a category, right? And black hole is also a category. Okay? So, we understand what black holes are, at least from philosophical point of view. But white dwarf, see, our sun, what it will become? Any idea about it? This sun will have a supernova in 4.5 billion years as predicted, right? And this, our sun, will change to a white dwarf. It will not change into a black hole, right? Because there is that kind of limit, there has to have that mathematical limit, right? When it crosses that limit, it turns into a black hole. When it does not cross that limit, it turns into white dwarf. So we can model the white dwarfs using the problem of particle in a three-dimensional box. Because in a white dwarf, what you have free electrons in a white dwarf. Now, so there are many more applications of this basic model in quantum mechanics. So, as we know that we have already discussed the problem of particle in a one-dimensional box. So what we are trying to do is we are extending this discussion to 3 dimensions. So if we do that, we have a starting equation, right? What is that? The basic equation is the Schrödinger's equation. So what is the Schrödinger's equation? So it is del square psi plus 2m by h bar square e minus v of psi equal to 0. This is our time-independent Schrödinger's equation. And this del square is what? It's a Laplacian operator. And in Cartesian coordinates, it's a Laplacian. It's a Laplacian operator. And in Cartesian coordinates, this del square is, it is dou 2 by dou x2 plus dou 2 by dou y2 plus dou 2 by dou z2. So I can write down Schrödinger's equation in 3 dimensions because I am talking about a particle in a 3-dimensional box. It has 3 dimensions. So I would like to write down this Laplacian operator in terms of its partial derivatives. So how would your equation look like? It will look like this: dou 2 psi upon dou x2 plus dou 2 psi upon dou y2 plus dou 2 psi upon dou z2 plus 2m by h cross square e of psi equals 0, because the potential inside the box is how much? The potential inside the box is 0. Now, this is a very complicated equation. You have 3 unknowns in this equation. And what we do here is we use a variable separable approach, right? What we do? We use a variable separable approach so that we can have some results from this equation. Now, what I do for that? I choose psi as a function of x of x, y of y, and z of small z. I will put a cross in small z. Okay? So psi has a dependence on x, it has a dependence on y, and it has a dependence on z. But what is important here is that this x of x does not depend on y, and y of y does not depend on z and x. So for x of x, y and z will act as constants. Getting my point? Okay. So now I can write down the double derivative directly. Okay. So what will be dou 2 psi upon dou x2? What will be that? That will be y of y, z of z, and d2. Now I will not use the partial derivative, right? I will use the total derivative as dou 2x by dx2. Clear? Okay, fine. So I can move on. Now, similarly, what we will have dou 2 psi upon dou y2. What will be that? That will be x of x and z of z, and then we will have d2 z by dz2. Okay. It has to be d2y. This has to be the capital Y, and this has to be the small y. Right? And the last one will be dou 2 psi by dou z2 is x of x, and then y of y, and then d2z by dz2. Clear? Okay? So I can use these double partial derivatives in the original Schrodinger wave equation, which we have written down in terms of 3 coordinates, which we have written down in Cartesian coordinates. And that would be, so I'll be writing, yeah, what was the first one? That was y of y and z of z, and then d2x by dx2. This would have been the first term, plus x of x, and then z of z, and d2y by dy2. Fine? Then plus x of x and y, it has to be the capital Y, so y of y and d2z by dz2 plus k square psi equals 0. Is this clear? Fine. Well, this k square is what? This k square is 2me by h bar. So this is our equation. This is our equation, and in this equation, what I will do is I will divide both sides of this equation by x, y, and z. Okay? So here, instead of psi, what should I write here? Come on. This is x of x, y of y, and z of z is equal to 0. This is how it goes on. So now what I'll do, I will divide both sides by x, y, and z. So what you will get, come on, can you tell me? You will get 1 by x of x, and then d2 x by dx2 plus 1 by y of y, and then d2 y by dy2 plus 1 by z of z d2 z by dz2 plus k square is equal to 0. Clear? Clear? Right. Now what is k? K is what? K is what? Come on. K is a vector. It's called a wave vector. And k is also equal to 2 pi by lambda. K has a relation with the momentum. Clear? So if k is a vector, suppose I have a vector r in 3 dimensions. This is x, this is y, and this is z. Okay? You have a vector r. What will be the magnitude of this vector? The magnitude of this vector will be, yeah, it will be x square plus y square plus z square. Now, similarly, k is a vector. And you define this vector in a 3-dimensional Cartesian space. So this k square will be what? What will be this k square? Come on, come on. So k square will be kx square plus ky square plus kz square. Clear? So I will write down the whole Schrodinger equation in terms of these Cartesian coordinates, where I have separated out each coordinate from this equation. So what I will have? I will have 1 by x of x, then d2x by dx2 plus 1 by y of y, then d2y by dy2 plus 1 by z of small z, then d2z by dz2, then plus, come on, plus kx square plus ky square plus kz square is equal to 1. Now you have the left hand side of the equation, and what is the right hand side of the equation? The right hand side of the equation is 0. So how will this equation make sense so that the result of the left hand side is equal to what? 0. So in order to get the result equal to 0, what I will say mathematically is this term plus kx square should be independently equal to 0. This term plus ky square should be independently equal to 0. And this term and kz square should be independently equal to 0. You see, we have boiled down a three-dimensional problem to three one-dimensional problems. And we have already solved the particle in a one-dimensional box. Clear? So this equation can be true only when these combinations will independently be equal to what? 0. So what will I write? Come on. So I will write 1 by x of x d2x by dx2 plus kx square is equal to 0. Now what does that mean? That means d2x by dx2 plus kx square of x is equal to 0. You remember? You had psi there in one-dimensional problem. You have x here, right? And what about another equation? 1 by y of y d2y by dy2 plus ky square is equal to 0. What does that mean? That means d2y by dy2 plus ky square y is equal to 0. Clear? The third one, 1 by z of z d2 z by dz2 plus kz square is equal to 0. That implies d2 z by dz2 plus kz square z is equal to 0. Clear? So you will have, in the similar fashion, you will be encountering those boundary conditions. You remember? At x equal to 0, psi is equal to 0. At x is equal to a, psi is equal to a. Got it? So you will be using the same boundary conditions and you will come up with the solution. So what will be the solution for three independent equations? What will be the solution? Come on. Have you written it down? Okay. So what will be the solution? Yeah? I have chosen a three-dimensional box with its length equal to a, its breadth equal to b, its height equal to c. You have three independent Schrodinger's equation along x, along y, and along z. Come on, tell me what will be the energy along x? Yeah, that will be n x square pi square h bar square by 2ma square. Clear? This will be your Ex. Come on. What will be Ey? Ey will be ny square pi square h bar square by 2m b square, because I chose the breadth of this box equal to b. What will be Ez? Ez will be equal to nz square pi square and h bar square by 2mc square. Clear? So what will be the total energy of this particle? Energy is simply a scalar quantity. So I can add up all the three energies to calculate the total energy of this particle. So what will be the total energy? So the total energy. So that is E. That must be equal to Ex plus Ey plus Ez. So total energy, E. What is Ex? Okay, I will write down that. I will write down pi square h bar square by 2m out. Inside, I will have nx square by a square plus ny square by b square plus mz square by c square. This will give us what? This will give us the measure of energy of the particle, right? And nx is your integral number along x, and y is your integral number along y, and z is your integral number along z. Clear? Now, if I boil down this problem to a cubical box, because that will give me a simple equation, right? So for cubical box, if I choose the box is cubical. If I choose the box is cubical, in that case, A will be equal to B, will be equal to C, will be equal to say L. Right? So what will be E in that case? E will be pi square h bar square by 2m L square. Right? L square is out, okay? Inside you will have what? nx square plus ny square plus nz square. Now this is your energy eigenvalues. These are your energies. But now, what will be the wave function? Because we are also interested with the wave function. So, yeah, come on. You remember the solution? You remember the psi for the one-dimensional problem? What was psi? Come on. It was? Yeah. You? What was psi? It was under root 2 by L sine of n pi by L times x. Right? But here we have three independent situations. And we have already defined psi as what? Psi is x of x, then it is y of y, and then it is z of z. Right? So what will be psi? Come on. So psi will be under root of 2 by a sine of nx pi by ax sine ny pi by by and sine nz pi by cz. But this under root 2 by a will be multiplied by, here you will have what? Under root 2 by b. Here you will have what? Under root, oh no. I should take it back like this. This is sine of nx pi by a times x. Then this is again sine. Okay, and this is again sine. I will do it here. Yeah, what will be psi? Come on. Psi will be under root of 2 by a, under root of 2 by b, under root of 2 by c. This will be your wave function for this particle in the three-dimensional box. So let me write it again. So this is psi is under root of 2 2s are 4, 2s are 8 by a, b, c, then sine of nx pi x by a, then sine of ny of pi y by b, and then sine of nz pi z by c. This will be your energy eigenfunction. Right? Now, see, you have calculated the energy eigenfunction for the particle in a three-dimensional box, and you have also calculated the energy eigenvalues, right? Now, if I say that I have an energy state, and corresponding to this energy state, if you have one eigenfunction, we call this non-degenerate energy state. What we call it? Corresponding to one energy state, if you have one eigenfunction, we call it non-degenerate energy state. Now, corresponding to one energy eigenstate, if I have more than one eigenfunctions, if I have more than one eigenfunctions, then I call it degenerate energy state. What I call it? I call it, so you have one energy state, and corresponding to this energy state, you have three different energy eigenfunctions. I mean more than one energy eigenfunction, then I say this is a degenerate energy eigenstate. Now at the same time, if I have one energy eigenstate and corresponding to this one energy eigenstate, you have n number of wave functions. How many functions? You call it n-fold degenerate energy state. You call it what? You call it n-fold degenerate energy eigenstate. Now you have a particle in a three-dimensional box. Now this particle can be in the ground state. This particle can be in the first excited state. This particle can be in third excited state. We would like to calculate the first two. I mean, say, when the particle is in the ground state, we will calculate its energy and we will see how many wave functions it will have. Clear? So, let's take on that. So, what was that energy equation? Come on, tell me. E is, was it pi square, h bar square by 2m L square times, we are choosing the cubical box here, okay? So then it was nx square plus ny square plus nz square. Now for ground state, for ground state. For ground state, what will be nx, what will be ny, and what will be nz? They will be all equal to 1. This is what ground state is called. Right? So what will be energy corresponding to that? Energy corresponding to that will be pi square h bar square by 2m L square. This is 1 square plus 1 square plus 1 square. Right? So 1 plus 1 plus 1 will give me 3. So energy will be 3 pi square h bar square divided by 2 m L square. Now this is my energy. This is the ground state energy of this particle. If this particle is in ground state, then what will be its wave function? What will be its wave function? Psi, nx, ny, and z. It will have one wave function, psi, 1, 1, and 1. Right? So this energy eigenstate is what? It's a non-degenerate energy eigenstate. It's because corresponding to one energy level, you have only one energy eigenfunction. You have only one wave function. So that's why this is my non-degenerate energy function. Now, if I take for first excited state, come on, for first excited state. Now see, for first excited state, is possible like this: 1, 1, 2, 1, 2, 1, 2, 1, 1. These are the possibilities. These are the possibilities for the first excited state. But if I will calculate the total energy, what will be that? That will be only 1. What will be that? So what will be the energy? Yeah? What will be the energy? That will be pi square h bar square by 2m L square times 1 square plus 1 square plus 2 square. In all the three cases, you'll have the same value. So what you will get here, yeah, come on. You will get E is equal to 1 plus 1 to 4 plus 2 is 6. So this is 6 pi square h bar square by 2m L square. But what about the wave functions? You will have wave functions psi 1, 1, 2, comma, psi 1, 2, 1, comma, psi 2, 1, 1. Now what is it? It's a degenerate energy eigenstate. So corresponding to the first excited energy state, you have three wave functions. So you will say, come on, this is degenerate energy eigenstate. Any questions? Come on. Any questions? So with this, I'll stop here. Okay. So bye. We have already talked about particle in a box. Actually, particle in a three-dimensional box. Let's try to build a couple of problems based on particle in a box. And what we have obtained is we have obtained the energy, and the energy is E, and E is pi square h bar square by 2m L square times nx square plus ny square plus nz square. So this is the total energy of the particle in a three-dimensional box, and the wave function that we have calculated is under root of 8 by a, b, and c, and then sine of nx pi by a times x, then sine of ny pi of y by b, and sine of nz pi z by c. So we have the energy, and we've already talked about the non-degenerate and degenerate energy states. If you rightly remember, the non-degenerate state means that if corresponding to one energy we have one eigenfunction, then we call this energy eigenstate as a non-degenerate energy eigenstate. And if corresponding to one energy eigenstate, we have a range of energy. We have a range of wave functions. We call it degenerate energy eigenstate. Now, if I choose a problem that in which I have, say for example, I have a three-dimensional box, and in this box I have an electron. I have an electron in this box, and if I have an electron in this box, then I know its mass. Its mass is 9.1 times 10 to the power minus 31 kilograms. And let me choose the length of this box, and assuming that this box is a cubical box, and if I choose the length of this box as, say, 2 nanometers, and 2 nanometers means 2 times 10 to the power of minus 9 meters, and I would like to calculate the change in energy. The change in energy, say from first excited state, to the ground state. So it's an open problem. All we have to do is to calculate. So I can calculate the energy of the ground state. In the ground state, I will have E. So E ground will be pi square h bar square by 2m L square times. So in the ground state, nx is 1, so this is 1 square plus 1 square plus 1 square. So the energy that we will obtain here will be pi square h bar square by 2m L square times 3. So I have 3 times pi square h bar square by 2m L square. Now, in the first excited state, what will be the energy? So I will call that E excited. Let me call it EE. That will be the same thing. Pi square h bar square by 2mL square times 1 square plus 1 square plus 2 square. So this will give me pi square h bar square by 2mL square times, it has to be square, times 6. So this is the energy of the first excited state, and this will be my energy of the ground state. So from here I can calculate the change in energy. So what will be the change in energy? That will be delta E. That will be energy of the excited state minus energy of the ground state. So this is the first excited state, and for first excited state what we have is, we have pi square h bar square by 2 mL square minus, it has to be 6 here, and And for the ground state, it's 3 times the same thing. So this is 3 pi square h bar square by 2 ml square. So what will be out? Pi square h bar square by 2 ml square times 6 minus 3. So this will be 3 times pi square h bar square by 2 ml square. And we can drop in the values, we can drop in the mass of the electron, and we can drop in the length, and we can drop in the value of pi, and we can drop in the value of reduced Planck's constant. So what will be that looking like? So delta E will be, it will be 3 times 3.14 whole square, then times 1.05 times 10 to the power of minus 34 joule second whole square, divided by 2 times mass of the electron, that is 10 to the power of minus 31 kilograms, and the length is 2 nanometers, so this is 2204 times 10 to the power of minus 18. Okay, so this is a big number, and when you calculate this, you will find that this delta E is, even though you will get this in terms of joules, and you'll divide it by 1.602 into 10 to the power minus 19, and you will get this change in energy will be nearly of the order of 0.12 electron volts. Now, what we would like to do is we would like to extend this same problem, but we would like to calculate the probability density. We would like to calculate the probability density of this particle at the center of this cubical box. So that's our next target. The target is that we want to calculate the probability density. If we want to calculate the probability density, then certainly we got to take the square of psi. And the square of psi will give us the probability density. But we want to calculate this probability density at the center of this box. At the center of this box. So we want to calculate it at the center. So the center means L by 2. So what's our wave function? Wave function is psi is under root of 8 by ABC, that's L cubed. And then you have sine of nx. You have sine of nx and pi x by L. And then again you have sine of ny pi y by L, and then sine of nz pi z by L. Now this is L cubed because it's a cubical box, so A is equal to B is equal to C, A is equal to L. Okay, so this is our psi, and if I apply the boundary conditions, what's the boundary condition in my problem is that I want to calculate this probability density at the center of this cubical box. So if I want to calculate it at the center of the cubical box, then along x I will have L by 2, along y I will have L by 2, and along z I will have L by 2. So so what will be psi looking like? So psi will be, so psi, the psi is basically of nx and y and nz, and the psi encloses all the 3 coordinates x, y, and z. So what will be this psi equal to? This will be under root of 8 by L cubed, and then you will have sine of nx, and then pi is there. Instead of x, I will have L by 2. So this is L divided by L times 2. This will be one thing. The next thing will be sine of ny pi, and then L by L times 2. And then sine of nz pi L divide by L dot Q. So because we have to calculate the probability density at the center of this cubical box, so we have a cubical box, and in this cubical box, this point is exactly L by 2 from the left, from the right, from the top, from the left, from the bottom. So that's why instead of X, I'm using here L by 2. Instead of Y, I'm using L by 2, and instead of Z, I'm using L by 2. So you can see this L and L will cancel, this L and L will cancel, this L and L will cancel. So what we know is sine of n pi by 2, this is all equal to 1. Because what we assume is that the particle is in the ground state, so what we will say is that sine of pi by 2 is equal to 1. So this will give me 1, this will give me 1, and this will give me 1. So the psi that we have calculated, is simply under root of 8 divided by L cubed. But what we have to calculate? We have to calculate the probability density. Now, in order to calculate the probability density, I will have to multiply psi with psi. So what I will have to do, so if I have to calculate this probability density, that will be simply psi square. So this psi is already calculated, so it will be under root of 8 by L cubed whole square, and square and root will cancel. So 8 by L cubed will be the probability density of this particle at the center of this cubical box. I think this does the work. We have already talked about the particle in three-dimensional box, where we calculated down the total energy of the particle in the ground state, then in the excited states, and what we did at the same time is we calculated the wave function for the particle in this three-dimensional box. So, bye.